Hello again. This is video lecture 15.1, and we are moving into a new area in our study of motion, very important area. We're going to study what are called oscillations. Oscillations, in a very general sense, is referring to any kind of motion that is repeating itself in a predictable way. So we're studying chapter 15, entitled Oscillations. And this lecture is all about Chapter 15, Section 1, in which we are going to introduce the most important kind of oscillation that we're going to spend pretty much the entire chapter focusing on. It's called simple harmonic motion. But let's take just a minute and build up to that idea. First key idea I want to mention. Physicists talk about periodic motion, which is also called harmonic motion. And that's any motion that repeats itself with a measurable repeat time. And that repeat time is called the period. And the symbol for period in periodic motion, the repeat time, is capital T. Please note capital T for the period in a periodic motion. Not little t for the variable time that a clock or stopwatch would read, and just as you go, just keeps going on and on and on. This is a constant capital T. Okay? It's the time for the completion of what's called one cycle of the periodic motion, and the SI unit is seconds, although I often talk about it as seconds per cycle, S over the word cycle, even though the word cycle is not a true unit, so I put it in quotes. Just to remind me, though, that what period is the time for a cycle, a period of the motion. This little photograph over here on the right side of the screen shows an old-fashioned child's toy, a paddle ball. It's got a wooden paddle and an elastic ball that's connected to the center of the paddle with an elastic string. And with enough practice, you can get to the point where you can continuously hit the ball with the paddle, and you'll hit the ball, it will travel outward, it will pull on that elastic string, stretching it, it'll slow, it'll stop for an instant, and then it'll come back and it'll hit the paddle again. And then it'll just repeat. And you have, if you've got enough dexterity to keep it going, you have periodic motion. I can show you a simple animation of that motion using a Wiley+ animation. Now here we've got a schematic, an abstract representation of the paddleball toy, in which the red dot that you see represents the ball. And the animation doesn't even show the paddle. You have to imagine the paddle is hitting that ball every time the ball is at the origin of that x-axis. And then what happens is when the paddle hits the ball travels outward in the plus x direction, slowing as it goes because it's stretching that string, that elastic string, and it'll reach some maximum distance from the origin, where the paddle is, and I label that in the animation x maximum. And as we'll learn, the maximum displacement from the 0 point is what's called the amplitude of the motion. And it'll go out to x max, and it'll come back to 0, and it'll just keep repeating. So let's run the animation and watch the paddle of the ball oscillate back and forth. Notice that it's moving slowly out at x max. In fact, when it's at x max, it is for one instant in time at rest, while it's moving very rapidly when it's near where the paddle is. Okay, so that's an example of periodic motion. In fact, what I can do is if I had a way to measure the x coordinate of the little paddle ball as a function of time, I wonder what that would look like. It must oscillate, vary between x of 0 and x equal to x max. And here is that plot. It's x, and I actually give you units, centimeters, versus t in seconds. Okay? And so you can see that the x coordinate rises, reaches a maximum, happens to be 10 centimeters, then goes back to 0, and then rises again, and so forth, and it just keeps repeating. And the animation here also shows me how to get the period. The period is the repeat time. So no matter where I put this slider T1, right now T1 is set to 0, it shows with this rightward facing red arrow exactly 1 period of the oscillation. So we go from time T1 to T1 plus 1 period, capital T, because that's where the graph starts to repeat. And I see that the length of that red arrow on the time axis is 2 seconds. So the repeat time for this motion is 2 seconds. And no matter where I put the T1 slider, that rightward pointing red arrow has a duration of 2 seconds and gets me to the next point on the graph that is at the same location. So no matter where I start, the period, the repeat time, is the same. In this case, 2 seconds. Okay, that's an example of periodic motion. The period then is the repeat time, the time to complete one cycle. Here's something we end up talking about with periodic motion, what's called the frequency F of the motion. The frequency F is the number of cycles completed per unit time. And in the SI system, the unit is cycles per second, although cycle isn't technically a unit, so I put it in quotes. And cycles per second is called the unit Hertz, H-E-R-T-Z. Has nothing to do with a rental car. It's the unit of frequency, denoted capital H, little z. So we'll talk about the period for periodic motion. That's the time to complete one cycle. And we'll talk about the frequency, F, which is the number of cycles completed, in SI anyways, per second. Let's look at the units then for period and frequency, including the word cycle to help us keep track of things. The SI unit for period is seconds per cycle, and the SI unit for frequency is cycle per second. Notice that those units are exactly inverted from each other. That's a clue for what is this very helpful tip to remember. Period and frequency are related in a very simple way. They are just the inverses of each other. The period of periodic motion, capital T, is just 1 over the frequency. They are inverses. In that paddle ball example that I showed you, the period of the motion, capital T, was 2 seconds, or if you like, 2 seconds per cycle. So the frequency F of that periodic motion in that animation of the paddle ball is 1 over 2, or 1/2, cycles per second. But nobody calls it that. People call it Hertz. So if the period is 2 seconds, the time to complete one cycle is 2 seconds, the number of cycles completed per second is 1/2. Since period and frequency are inverses of each other, no matter what kind of periodic motion you're talking about, if one number is big, then the inverse is small. So if the period is a very big number, it takes a large amount of time to complete one cycle, then the frequency is very small. Not many frequencies per second. The period is very small, then the frequency is very large. The inverses of each other. That's a very helpful thing to remember. Okay, so generally speaking, periodic motion is any motion that repeats itself with a measurable repeat time constant called the period. But now let's focus on a little bit more restrictive kind of periodic motion, and it's called simple harmonic motion, which I'm going to abbreviate SHM, simple harmonic motion. It is a special kind of harmonic motion, and what you mainly got to remember is our picture here for the standard system that undergoes simple harmonic motion. horizontal, frictionless surface with a block and a spring. Block has some mass m, spring has spring constant k. We have an x-axis along that horizontal frictionless surface. No friction here. If you want to learn how to study periodic motion when there's friction on that surface, take Physics 310. Frictionless horizontal surface, we put an x-axis on there. Note x equals 0 would be at the point where the spring is unstretched. That's where the block would rest if you put it there. So we'll call, as we would have when we studied motion with a spring before, x equals 0 is equilibrium. Remember, the spring exerts, when it's stretched or compressed from its natural length, a spring force, and the spring force obeys Hooke's law. We need to remember that. Okay? So the standard block and spring system is the canonical example of a system that moves with what we call simple harmonic motion. It is the most important kind of oscillation, the most important kind of periodic motion that there is. We need to understand everything there is to understand about simple harmonic motion, and I do mean everything. First, let's just get a visual, make sure we're clear on what this is going to be doing. If I put that block right at x equals 0, spring is not stretched or compressed, and let go, what would I see? Nothing, right? If I put the block right at x equals 0 with the spring unstretched and uncompressed and let go, nothing will happen. No movement at all. The block's at equilibrium. That's pretty boring. That's not simple harmonic motion. We need to get this block moving somehow and then see what kind of motion we get. There are, generally speaking, 3 ways to get this block spring system oscillating. And I'm going to tell you those right now, and I want you to get used to the notation we're using. Remember, this block is going to be moving along an x-axis. So at any given time, I would like to know what its x-coordinate is. Also, I'd like to know what its velocity is. Also, I'd like to know what its acceleration is. Now, let's take the first dot here. Here's one way to get this system oscillating. What does this set of symbols mean? X with a 0 in parentheses. That means that we're talking about the value of x at the time t equals 0. It's in parentheses because x is a function of t. So the number in the parentheses is the time value. So when we write something like that, we mean the x-coordinate of the block at time 0. And so what I'm showing you is one of the ways you can get this whole block spring system oscillating is have the x-coordinate be 0, but look at the next symbol, v with a 0 in parentheses. That means we're talking about the velocity of the block at time 0. Have the velocity not be 0. So that means the block is just sitting at the origin, and you reach in and you shove it so that you give it an initial velocity at time 0. Then it will oscillate. Okay? Let me show you that with another Wiley Plus animation. Now I need to get the picture that I want to show you. Okay, there's the picture. Now this is a very content-rich animation because it allows us to control a lot of things, including the time on the animation. But the key sliders are V. Now there I've written V sub 0 in meters per second, but that means V initial. And X sub 0, X initial in meters. So I'm starting out with V sub 0 not 0, V initial not 0, 4 meters per second, and X initial 0. And so then look at that block down there on that spring. Look where its edge is right now. It's at equilibrium. So its X initial is 0, but look at that red arrow to the right. That's its velocity. When we're starting all this, its velocity is to the right. So when I run this animation by running the t up there, the block's going to oscillate. Okay, so first just watch that. It oscillates to the right, then to the left, then back to the right, then back to the left, and so forth. And it would repeat this forever, ad infinitum, because remember, we're assuming no friction along that x-axis. And the red arrow is the velocity, v, and the second arrow, which is a kind of a light blue, is the displacement from equilibrium, x, and the darker blue arrow is the spring force. Okay, but now that's one way to get that whole thing moving. It starts out at an initial x of 0, but an initial velocity that wasn't 0. And notice what else the animation did. It plotted the x coordinate, which is also the displacement from equilibrium. It's a function of time. And that's this purple trace. For comparison, in the second graph, I have what we'll just call an unshifted cosine, a plain old simple cosine curve. And you can see that the actual x versus t graph here in purple isn't the same as an unshifted cosine. For now, I just want you to note that. All right, now let's go back to this slide because I want to show you a different way to get this whole system oscillating. You ready for another way? It's the second line right here. The second line says this: have the initial x value not equal 0 and the initial velocity value equal 0. That means just take the block, pull it away from equilibrium, stretching the spring a bit, and just carefully let go. Then x initial is not 0, but v initial is 0. That will also get it oscillating. Let's look at that on the animation. So let me reset. Let me go into the v initial value and put 0 there. And let me take the x initial and make it as big as I can, 5 meters. This is a big block system. So now the block's out at 5 meters, and I've just let go with no initial velocity. Let's watch the motion. It oscillates to the left, stops, oscillates to the right, stops, and repeats. And it will do this forever. Okay? And look at the plot of x versus t. It is exactly the same as an unshifted cosine in that case. All right, now there's a third way, in general, to get the whole block spring system oscillating. And it's the most complicated way. It is to have both x initial and v initial not equal to 0. So that would be done by taking the block, pulling it from equilibrium so that x initial is not 0, and, just as you let go, giving it a shove so that its initial velocity is also not 0. So let's show that on the animation. So I'll reset. I'll keep the x initial at 5, and I'll make the v initial at as big as I can, 4 meters per second. So now the animation shows at time 0 that the block's out at 5 meters, but see the red arrow to the right? It's also going to have a velocity to the right. So when I run the animation, note it's going to start at time 0 moving to the right. So note, to the right, then back to the left, then back to the right, then back to the left. Okay? And it will repeat that forever. Note the trace of x versus t up above. Wow, that's definitely not the same as that unshifted cosine. It's definitely a cosine curve that has been shifted left or right. We're going to need to be able to deal with that business of how has that cosine curve been shifted there. All depends on what we call initial conditions are. Okay, so all of these different situations that I've listed here are 3 different examples of what we call initial conditions of the system. Initial means what's happening. Initial conditions means what's happening at time 0. Initial. Okay? And depending upon the initial conditions, that will affect exactly what shape the trace of x versus t has. All right, well, let's move on for now. And we're going to continue studying the block on the spring. And let's apply Newton's second law to it. Right? We're going to go back to Newton for a little while, but we're going to focus on, well, just what I've said. The quintessential, the canonical example of the simple harmonic motion system, horizontal block spring on a frictionless surface. So we're going to apply Newton's second law, translational version, to the block. Nothing's rotating here. So we're back to our old friend, A sub x equals F net x over m. Note, there is only one x force right there. I'm showing the block displaced a bit from equilibrium so that the spring has been stretched. It's the spring force. Remember, the spring force is given by Hooke's law. And for the one-dimensional case, F spring, where the equilibrium points at the origin of the x-axis, is negative kx. Negative sign is important because the spring force is always opposite to the displacement from equilibrium. This picture shows a block displaced to the right, and the spring force is to the left because it wants to bring the block back to equilibrium. Hooke's law. Please don't forget that, old friend. That's the formula for our spring force. So we put that in the next line where the F net x is. A sub x equals negative kx over m. Now all I did next was a little grouping. I grouped the k over the m together in parentheses. So I have a sub x equals negative k over m times x. Now, you got to imagine that that block and spring system is oscillating. See the little shading to the right of the block? That's trying to represent motion. Plus, I showed you the animation. Got to imagine the block and spring oscillating back and forth, back and forth. So as we're watching, please note, the value of x is changing, right? The block is at different x values at different times. So the x is not constant. But k is the spring constant. That doesn't change. And m is the mass of the block. That doesn't change. So the k over the m part, not changing. X, changing. So, given this formula we've got, a sub x must be changing. So what we've got is an equation that has this form. Acceleration equals negative constant times displacement from equilibrium. Okay? Because that's what I've got up here. Acceleration equals negative constant times displacement from equilibrium. Here's a really important tip. Anytime when you apply Newton's second law, you get an equation of that structure, the acceleration of the system equals a negative constant times displacement from equilibrium, then you know that that system is going to move with what we call simple harmonic motion. Even if the actual system that's moving doesn't look even remotely like a block and a spring. That's an important thing to remember, as we'll see later on in the chapter. But for now, we are focusing on a block and spring, and we have applied Newton's second law, and we've got a pretty basic equation for the block and spring's acceleration. The structure of that equation is my point. It's the structure of that equation is acceleration equals a negative constant times displacement from equilibrium. And the constant here is given by the value of the spring constant divided by the mass of the block. All right, now I'm going to do something. I'm going to take another old idea for us. I'm going to remind us that by definition of acceleration along an x-axis, I can write a sub x as the second derivative of the x-coordinate with respect to time. By definition, a sub x is the first derivative of the x velocity with respect to time. But the x velocity, v sub x, is itself the first derivative of the x-coordinate with respect to time. So this says take the derivative of x with respect to t, and then turn right around and take the derivative with respect to t again. And a mathematician calls that a second derivative of x. and denotes it like that. Don't say dt squared, just say second derivative of x with respect to time. Now, we never wrote acceleration like that when we were applying Newton's second law, did we? As a second derivative of x. But we could have, if it had been useful. It never really was useful up until now. So all I've got here is just another way to write Newton's second law for that block and spring. Although it looks very different from anything you might have seen before, it is still just Newton's second law. And it says that the second derivative of the block's x coordinate with respect to time is equal to a negative constant, k over m, times the displacement from equilibrium, x. That is Newton's second law. However, to a mathematician and to a physicist and to an engineer, this, the way it's written now, is supposed to make us think of what is called a differential equation. What the heck is that? Well, it's an equation, see the equal sign, with a derivative in it. Now this has got a second derivative, doesn't it? So what we call it is a second order ordinary differential equation. We'll learn about other more fancy differential equations later, and many of you will take an entire course, maybe even more than one, on solving differential equations. That's how important it is in physics and engineering. So Newton's second law here has given us a second order ordinary differential equation, where we're taking a derivative of the function x, and it is a function of t. And the whole purpose of a diff-EQ is to solve. What would you solve for in this case? You would solve for x as a function of time. Okay? Now, like I say, when you take a diff-EQ class, you will learn formal techniques for solving this diff-EQ. It is one of the most important differential equations in nature. But I'm going to show you a way to solve this diff-EQ, which is a perfectly valid way, although mathematicians probably don't want to talk much about it. But physicists and engineers will do it all the time. And that is, guess a functional form for the solution. Now, where the heck is that coming from? Why is that even allowed? Well, I don't mean guess in a frivolous sense. Just make something up and say, that's the solution, I made it up, I'm going to pretend. No, 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 I don't mean that at all. I mean, try to use some kind of mathematical intuition to predict what the correct solution to the differential equation is. And I contend, believe it or not, that it's not that hard to predict what the correct functional form of the solution to this differential equation is. How can I possibly make such a prediction? Because the differential equation, whose solution I'm searching, says this: I must have a function x of t. If it's going to be my x of t is going to be a solution to this diff-EQ, I must have a function x of t such that when I take two derivatives of that function with respect to time, I get a negative constant times that same function back again. Let me say that again. The functional form x of t that's going to solve this diff-EQ has got to be a function such that function x of t, when I take two derivatives of that x with respect to time, I get a negative constant times the same function I started with. There are not many functions that fit that. It's very restrictive. For example, I can tell you right now that this would not be a solution. X of t equals 3t squared. That's a function of time. Because when you take two derivatives of that, you don't have negative constant times 3t squared again. There's no way. Okay? It's got to be a function such that when I take two derivatives I get a negative constant times the same function I started with. It's really worth your time to puzzle through what function that might be. But of course, the slide shows you, so I'm not going to force you to. The functional form we're going to pick is what we call a general solution, and it's this form right down here. It's a cosine. We could also pick a sine. There is fundamentally nothing wrong with the sine, but we're going to pick a cosine because it's what your book uses. Why? Why am I picking a cosine? Don't worry about everything in that answer, just why it's a cosine. Because what's the first derivative of cosine? Negative sine. Now take the derivative of that to get a second derivative. What's a derivative of sine? Cosine, but it had a negative. So negative cosine. Negative with the function I started with. Same's true with sine. What's the first derivative of sine? Cosine. Take the derivative again, what do you get? Negative sine, the negative of the thing I started with. Now, some of you might be thinking, why don't you take a function of this form? E to the t. Depends on how much you know about derivatives. What's the first derivative of e to the t? E to the t. Isn't that an amazing derivative? What's the second derivative? E to the t again. Isn't that okay then? I'm back to what I started from. What's wrong? No negative sign. You can't ignore that negative sign. It comes from Hooke's law. So e to the t is not going to work. Now, just to give you a little bit of a teaser for more advanced study, there is a form exponential function that will work. Do you know the imaginary number I? Which is the square root of -1. You must have seen that in advanced math / pre-calc. How about the function e to the it? Wow. The argument of the exponential is I times t. What's the first derivative? You got to use a chain rule. I times e to the it. You bring down an I. Turn around and take another derivative. I squared times e to the it. But I squared is -1, so negative e to the it, the negative of the function I started with. So that form will be okay, but we're not going to use it. Back to what we're going to use in this book for the general solution of simple harmonic motion, right there. X of t equals a cosine bt plus phi, where a is just a constant, b is a constant, and phi is a constant. We're going to have to figure out how to determine all those constants, okay? But first, I'm going to show you how that prediction of a solution is acceptable. It does solve this diffie-q. Whenever the physicist or engineer makes a prediction as to what function is going to solve a diffie-q, what they do is they substitute that function back into the diffie-q to show that the two sides of the resulting equation can indeed be equal at all time values. So we're going to verify that this function is indeed a solution by substituting it back into the differential equation. All right, now to do that, I have to take two derivatives of x with respect to t and substitute the answer for that on the left side. So let me do those two derivatives. We need to be able to do this. I have to do it in 2 steps. The first derivative right here, we need the chain rule, because what I have to differentiate is a times cosine blob, where blob stands for bt plus phi. So what do we get when we differentiate a times cosine blob with respect to t? Well, derivative of cosine blob is, chain rule, negative sine blob times the derivative of the blob. So, negative sine blob, and the derivative of the blob means take the derivative of bt plus phi with respect to t. All that survives that is b. So there's where that b comes from. And of course, the a here was multiplying the cosine out front. That just gets carried along. You do need to be able to do that derivative. So if you have to think about it more, that's fine. but you do need to be able to do that derivative. So there's our first derivative, negative b times a times sine blob. Now I've got to turn right around and take a derivative of that so that I have two derivatives. Derivative of sine blob is cosine blob times the derivative of the blob. All right, so that's why the sine blob becomes a cosine, and the a is still there, and the negative is still there, but now the b is a b squared. And now we substitute that expression to the left side of the differential equation and rewrite the entire equation. So here we go. There it is, the top. Negative b squared a cosine blob. That's from the second derivative. Okay? Now, what's on the other side? Well, what I had in the equation. Negative k over m times x. The only thing I do now is I plug in the functional form for x. So now you see negative k over m, and then there's the expression, which was our prediction for the solution for x, a cosine blob. Now, I want the two sides to be equal no matter what the little t is. Little t is the time variable, always ticking away and changing. Okay? So, what has to be true in order for both sides to be exactly the same at all times? Well, let's see. I got a negative on both sides. I got a factor of a on both sides. I got a factor of cosine blob on both sides. It's all looking good. But I do see that one thing has to be true if the two sides are going to be equal. This part has to correspond to this part, because those are the only things that are different on the two sides. So in fact, I'm going to demand that b squared be equal to k over m. Then the two sides will be the same. Nothing back here in my prediction for the functional form, nothing back here in my prediction said anything about what that constant b was. Nothing. Now I know, in order to be a solution to the Diffie-Q, that constant b is restricted. It must be equal to square root of k over m. Oh dear, excuse me. That constant b in my prediction of my solution is determined by two things, the spring constant k and the mass of the block. And note b then is the square root of k over m. Okay, so our functional form is this, where now I know that constant b can't just have any old value. It is set to be equal to the square root of the spring constant over the mass. Now, to get you used to some of the names here, the argument of the cosine, the whole thing there, is called the phase of the solution. And it will be in the SI unit called the radian. So, heads up, for this chapter, pretty much you might as well put your calculator in radian mode and leave it. Because we will be taking cosines of things and sometimes sines of things, but we're going to be working in radian mode. Now, just so you're used to the notation, I could just keep calling that constant b that multiplies the time variable b. Perfectly legitimate thing to do, but none of the books do that, and there's physical reasons for it. The books use the symbol and a name for this constant. First, a symbol. Symbol used in chapter 10 in rotational motion. Instead of b, they use the symbol lowercase Greek letter omega. So I'm just renaming the symbol b to an omega symbol. Still square root of k over m. Here's its name. Angular frequency, when you talk about simple harmonic motion. And the SI unit is radian per second. So, the angular frequency of the harmonic motion is determined by square root of k over m. Now I'm going to tell you a little bit of a tip. I'll show you where it comes from, okay? But I'm just going to tell it to you now, and it's very helpful to remember for this chapter. There is a very simple relationship between this new constant we've just come across, called angular frequency, symbol omega, and a constant we've already talked about for periodic motion, the period, capital T. And that relationship is right here. The angular frequency omega is equal to 2 pi, with the unit of radian on that 2 pi, over the period. That's it. The angular frequency not only is equal to square root of k over m, but it's also equal to 2 pi over the period. I'll give you a little bit of an idea where that comes from by looking at this formula in just a minute, by looking at this formula right below. Okay, but let me finish off with some names here. Okay, so now the symbol I was calling B and is given by square root of k over m is going to be given by the symbol omega, and it's called angular frequency. The constant that I've called capital A out front is denoted by x sub m, and that represents the maximum displacement from equilibrium, and it's called the amplitude of the motion, and the SI unit is the meter. Right? Because the number multiplying the cosine is going to be, since the biggest the cosine can be is 1, the biggest the x can be is whatever the number is out front of the cosine, and we're going to call that maximum displacement from equilibrium the amplitude. So xm for max instead of a. The m is supposed to help us remember maximum displacement. That's what amplitude means. And the only other constant that I haven't talked much about is this phi that's added on to the omega times t. Phi's name is phase angle. Its SI unit is the radian because it's inside the argument of the cosine. And I'll just give you a heads up that phase angle is generally what gives us the hardest time understanding its meaning. But basically the phase angle phi says, how much have you taken a simple cosine curve? Simple cosine curve is a curve that peaks at time 0, where cosine should peak, and it takes that cosine curve and it just shifts it left or right. That's what the phi, the phase angle, does. Okay, so here's the new way now we're going to write the formula for the displacement of the oscillator from equilibrium as a function of time. X of t equals x max, that's called the amplitude of the motion in meters, represents the maximum displacement from equilibrium, get that up a little bit higher, times cosine of another constant, omega, called the angular frequency in radians per second. T is time in seconds. Then add on a final constant, phi in radians, called the phase angle. Now the last thing I want to show you is where this relationship between angular frequency, omega, and period, capital T, comes from. It comes from the basic idea of what we mean by period of periodic motion. It means the repeat time. So if I take the displacement at some time t, and I add to that time little t, the period, big T, the block has to be at the same x it was at the beginning of that period. So x of t plus big T must equal x of t, or to say it even more clearly, x of little t plus big T must equal x of little t for any little t. So that means x max cosine of omega t plus omega big T plus phi must equal x max cosine of omega t plus phi. Two sides must be equal. The only place there's any difference between the two sides is this plus omega times big T. But I know when the cosine repeats itself. It's when its argument increases by 2 pi radians. And that's what's happened here. We've increased the argument of the cosine so I get going through just one period, one cycle. So it must be that omega times big T equals 2 pi radians. So the angular frequency omega is 2 pi radians over the period. All right, now let me show you a little bit more about these various properties of the solution to simple harmonic motion by going back to an animation. Now I want to show you this one, which is just the plot of the solution that I just showed you. It's a plot of x in meters versus time in seconds. The functional form is x max cosine of omega t plus phi, and the sliders up above let me control x max, omega, and that should be a phi symbol. X max in meters, omega in radians per second, and phi in radians. So I'm going to change them one at a time. I'm going to increase each one at a time. I want you to predict how the graph's going to change. So I'm going to take the x max at 1 meter, and I'm going to increase it. I want you to make a prediction in your mind how the graph's going to be affected. Pause the video if you need to. Okay, how is the graph going to change when I increase x max? It gets taller. Because we're plotting x versus t, x max is the biggest x. I've gone up to an x max of 4, so the graph has to go up to plus 4 on one side and minus 4 on the other. And this represents a block that's oscillating plus 4 meters to the right of equilibrium and 4 meters to the left of equilibrium. All right, now let's keep x max where it is. Let's increase the angular frequency omega. It's currently 1 radian per second. Let's increase it. Pull that slider to the right. How's the graph going to be affected? I'd like you to make a prediction. Pause the video and then come back. All right, let's see what happens when we increase the angular frequency. Aha. Notice that it oscillates more rapidly. That's one way to say it. Okay, it oscillates more rapidly. Another way to say it is the period got smaller, didn't it? The time for one cycle got less. And angular frequency omega and period are inversely related. So if the omega got bigger, the period had to get smaller. So the bigger the angular frequency, the more cycles per second, the shorter the period. Now let's slide the phase angle phi in radians. It's currently 0, so we have what I call a simple cosine. And you'll notice that when time is 0, the plot is at its maximum, just like cosine is. Cosine of 0 is a maximum, plus 1. So the cosine curve is a simple cosine with having its maximum value at time 0. That's because the phase angle phi, this is a phi value, is 0. Now I'm going to drag that slider to the right, making the phase angle positive. What's going to happen? This is probably harder for you to predict. Well, if I drag the slider to the right, making the phase angle positive, the curve shifts to the left. So a positive phase angle shifts the curve to the left. If you like, the peak that was happening at time 0 when the phase angle was 0 is now occurring earlier than time 0. I'm just about at a phase angle of pi over 2 radians. Notice the curve looks like a negative of a sine curve. If I go all the way to the maximum, I'm at pi radians, and I've gone from a cosine curve to the negative of a cosine curve. That's a phase shift, phase angle of pi radians. Now we go back to 0 here. There we are. 0 phase angle. We have a simple unshifted cosine. What if I drag the slider to the left? That's going to give me negative phase angle. Then the curve goes to the right. There I am at negative pi. Okay? All right, so that's some practice with x max, omega, and phi. Amplitude, angular frequency, and phase angle. Okay, that's our first video. So I'm going to pause here so that you can pause. And then we're going to have a second video where we're going to still study a little bit more this solution, this function x of t for simple harmonic motion. It is so important. We're going to spend lots of time with it. But that's all for this first video.